Hello everyone, this is Joshua again, and today we are going to be discussing data visualization. So for the last few videos, we've discussed ways to summarize data using numbers. We have used measures of central tendency and measures of spread. But sometimes it can be helpful to actually see your data in addition to having numbers to describe it. Data visualizations are important to understand because you'll see them every day in the news, on Facebook, or even in magazines. There are two main types of data that we might encounter. There is the categorical data and there is the quantitative data. Quantitative data are quantities or numbers that have both ordering and consistent spacing. For example, how many ounces of olive oil are in each American home? If three families told you how many ounces of oil they have, you could put them in a meaningful order, from least to greatest or greatest to least. This order has consistent spacing. An increase in 1 ounce of olive oil is the same whether you go from 0 to 1 ounce or from 100 to 100 ounces. These properties allow us to do simple math with the data, like taking the mean or calculating the standard deviation. Categorical data doesn't have a meaningful order or consistent spacing. For example, favorite kind of pasta. You might like penne, rotini, linguine, or even angel hair, but there's no objective way to put those pastas into a meaningful order. The simplest way to display categorical data is to make a frequency table. A frequency table shows you all the categories and the number of data points that fall in that category. In other words, it's frequency. To change a frequency table into a relative frequency table, we just need to take each raw frequency and divide by the number of the total points to get a decimal between 0 and 1. Some of you may be used to reading decimals as percentages, but if you're not, just multiply by 100 to get the percentages. For linguine, we have 10 divided by 50, which is 0.2 or 20% of the group. Relative frequency tables have the benefit of being easy to compare. No matter what we're measuring or how many data points we have, it's easy to compare percentages. If 20% of people like linguine, we can see that's a smaller percent than the 67% of people who like pineapple on pizza, or greater than the 10% of families who thinks statistics is hard. The relative frequency table for favorite pasta might look like this. We can also add more than one variable to our frequency table. We could ask people to rate their favorite pasta sauce and make a combined frequency table or a contingency table of both pasta and sauce preference. If I were planning a party and needed to pick some pasta for the group, my best bets would be rotini with red sauce and penne with red or white sauce. And because I'm planning a party and because I'm having food, the chance of death by choking on a food in the US in a given year is 1 in 100,686. But sometimes we don't want just numbers in our visualization. Earlier in the series, I talked about how it can be hard to wrap your head around numbers, especially when they get really big or really small. There are other more visual ways to represent a categorical data. One way to do this is with a bar chart. A bar chart uses the frequencies that we saw in our frequency table to create bars that have a height equal to the frequency. That way, we can compare the height of the bars instead of looking at raw numbers. Here's a bar chart that represents the pasta data we saw in our original frequency table. You can see that penne is by far the most chosen pasta and how it compares to angel hair. Bar charts display a lot of information in a very simple graph. They can also display the frequencies of multiple variables. Let's say we want to compare each of these pasta types with either white or red sauce. We can either stack the frequencies so it gives us the same information as our contingency table. Or we can have bar charts side by side. Pie charts are another way of displaying categorical data. They use the relative frequencies of categories to portion out pieces of a circle, just like a pie. The higher the relative frequency, the bigger the slice of a pie category gets. Pie charts are useful because our eyes are pretty good at comparing slices. Our pasta data in a pie chart looks like this. Pie charts are great at visually displaying one variable, but they struggle to effectively display more than one variable like our pasta and our sauce contingency table. Another way to display categorical data is a pictograph. Pictographs represent frequency with pictures. A picture, like the ball in this basketball participation graph, will represent some numbers of units, say 100 kids. So if Riverdale High had 550 students participating in their basketball programs, then the graph would show 5.5 basketballs. Sometimes pictographs represent frequencies by increasing the size of the picture instead. And it's not wrong, but it's more difficult for us to visually compare, especially small differences, which can be misleading. Plus, at a casual glance, we don't know what the size difference means. We don't know if we are comparing the diameter of the basketball or we are comparing the areas. Data from the US Department of Education shows the graduation rate has been climbing. We can see that the stacks of books are not proportionate. It shows a difference of 5% from 75% to 80% with a stack of books that is over double the height of the 75% stack. This makes the difference seem huge because the axis doesn't start from zero. And yet, an increase of 80 to 81% is shown by the two stacks that are barely different in height, even though the 5% difference looks huge. Always keep an eye on those axes. Let's look back to the quantitative data, which, as you will remember, have a meaningful order and a consistent spacing. Frequency tables can be used to display quantitative data like age, height, or even ounces of oil in your house. We just have to create categories out of our quantitative data first. We do that with a process called binning. Binning takes a quantitative variable and bins it into categories that are either pre-existing or made up. For example, I can say that 0 to 15 ounces of olive oil is very little, 16 to 32 ounces is average, 33 to 49 ounces is a lot, and 50 plus ounces is excessive. Once I've binned my data, I can create a frequency table or a relative frequency table just like with our pasta example. It might look like something like this. Binning is most useful when there's pre-existing bins for our data. Like you can divide age in years into bins, child, teen, adult, and other adult because those are pre-existing categories. We can also take a score on a depression test and create two bins, clinically depressed and not clinically depressed. You can see from this example that bins don't have to be equally spaced. But if you see quantitative data that has been binned, make sure that the way it was divided was appropriate for the situation. Unequally spaced bins can be misleading unless there's a real-world distinction to back it up. Say politician X wants to make himself look popular, but it seems that the people in their 30s really hate him. Politician X wants to hide the fact that over 80% of people in their 30s said they won't vote for him. So he does some rebinning. Traditionally, the data are binned roughly by decade, 18 years old to 29 years old, 30 years old to 39 years old, 40 to 49 years old, and so on. But Mr. X needs to hide these 30-somethings in the data. The old chart looks like this. But politician X needs to split up the 30-somethings to make his numbers look better. He moved the data around to hide the glaring group of 30-year-old dissenters. Instead of showing the truth that the 30-somethings despise him, we see a more positive view of his popularity. By splitting the 30 somethings and putting some of them into two other larger groups, we can obscure their political dissatisfaction. Looking at his new table, he'd win the popularity vote in each of the five new bins. If I don't show you the numbers of voters per bin, it seems legit. Another categorical graphing method we can apply to the quantitative data is bar charts. When using bar charts for quantitative data, we squish the bars together so that they're touching and we call them histograms. The bars are squished together because the data are continuous, which means the values in one bar flow into the next bar, there's no separation like in our categorical bar charts. In histograms like bar charts, the height of the bars tell us how frequently data in a certain range occur. A histogram also gives us information about how the data is distributed. We can estimate where the mean, median, and the mode of our data, as well as to see how spread out the data is. Look at this histogram for our olive oil data. For this histogram, we can see that the range of the data is approximately 85. Since it covers the value 0 to 85 ounces and it is skewed to the right, its center is around 25 ounces. The histogram gives us more information about the data than a frequency table does, but they are still obscuring what the specific data values are. If you read the news or watch the news, you will see these representations over and over. You will likely see far more than these charts and graphs that you will create. The big takeaway here as a consumer of these things is to look closely at what the visualization is actually telling you, or maybe trying to hide from you. These charts and graphs give us another way to comprehend numbers, to see the big picture. Okay, everyone, that was the end of our discussion. I hope you have learned something. Thank you so much for watching and be safe.